Hi, and welcome to this 16th class of the Computer Vision course. My name is Javier Selva, and today we're going to be looking at transformer models. So maybe you have already heard about these models from the natural language processing subject, and I'm going to be using some examples from the natural language perspective because transformers were born as a machine translation mechanism. So it's going to be easier to understand where do they come from if we look to recurrent models from natural language. Then we're going to try to solve some of the limitations of the recurrence model with attention mechanisms, and these attention mechanisms is what is going to give rise to the transformer model. We will see the transformer, and in particular we will delve into the dot product attention, or this self-attention operation which is based on query, key and value. We will see that in a bit. And then we will jump to the specifics of computer vision transformers, basically on how do we train these transformers and some designs to be more efficient when handling the high dimensionality of visual input of images and videos, etc. Finally, we will see some examples of applications of transformers for vision, and that is going to be it. So let's start this off. First of all, you already saw some weeks ago about recurrent models, and you saw that we had to input one element of an input sequence at a time, right? So first one element, then we create a representation space, then the next element, and so on. So it's a sequential model, right? Every element comes after we have already used as input all the previous elements. So this is going to have some limitations. First of all, distant elements are going to be super hard to relate because we are going to have a lot of intermediate steps that are going to dilute the information from this element to when we are going to need it at the output up here. So there's going to be a lot of operations in between. And also, it's not going to allow us to parallelize operations because we need to perform one after the other. So this relating distant elements is going to be problematic because we're going to need a whole lot of new operations, and this is going to be a problem also when training the model. When we want to backpropagate information, it's going to be hard to backpropagate through long sequences. That's why we need a truncated backpropagation, because otherwise, if we try to fully backpropagate, we have the vanishing radius problem where information gets lost in the process. And another of the limitations, and especially in sequence-to-sequence model, that when we have an input sequence and the output has to be another sequence, is the problem of having a fixed length representation. But we have this problem as well when we want to classify, right? So if we have an input sequence that has 5 elements, and if we have an input sequence that has 20 elements, the output representation is going to be exactly the same. So we're going to have a representation problem. When we have many elements, we're going to be losing a lot of information. So in order to solve this, we're going to try to be using an attention mechanism. An attention mechanism basically what does is to select important regions of an input. In this example, for instance, this attention map that's overlaid over these images is trying to tell us which pixels of the image are the most important when we're trying to detect a bird. If we're trying to tell apart which images contain a bird, we should be looking very hard to these pixels because they are going to be the most informative when trying to decide if there's a bird on an image or not. So basically, this is what an attention mechanism does: select important regions. So in the context of recurrent models, the first, one of the first, or the one that inspired the transformer is going to be this model where instead of grabbing the output of the recurrent model to be using that information, we're going to be using all of the intermediate states of the sequence. So now imagine we have this sequence-to-sequence model, right? Where we want to input a sequence of pixels, which are going to be all the pixels from these 3 frames, and we want to generate another sequence, which is going to be the sequence of pixels of the next frame, of the future frame. So instead of taking the output of the last state with a fixed representation, we're going to be using all intermediate states. But that's a lot of information, that's too much information. So we need some attention mechanism to tell us how important each intermediate state should be to create this context vector, right? So what we're going to do is to take all of the intermediate states and we're going to be weighting them somehow. So some states are going to be more important than others. Here in the image, these orange arrows are representing the most important intermediate states. So we should be looking mostly at this point and at this point and all these points here. We are going to be looking at all of them, but mostly we should focus on these intermediate states. These are going to be the most important ones to decide to generate the next pixel, right? So how are we going to do this? These weights are going to be defined by a score mechanism. This is going to be the attention operation, right? Which is going to tell us, given the previously generated state, the state we already generated, and given all the intermediate states, how much should each state contribute to the context that is going to give us the information relevant to generate the next step. So we can do this in several ways. This work in particular, what they did was to use was to train a network that, given all the intermediate states and given the previously generated state, we want to predict a weight for every one of these states, right? But this is going to have learned weights. So we're going to be using a learned representation, right? So we're going to be using an already learned relationship of the states to predict these weights. Now, this is a non-local operation. What does this mean? So in convolution, when we were looking at convolutions, what we had is that the representation of the next layer of an image is going to depend on the interactions of a small neighborhood, right? So we had these small filters, and in order to select what the representation of this pixel is going to be, we're going to take information coming from these 9 pixels. This is a local operation, right? And a local operation is one where we take into account every element in the input when deciding the next representation. So this is going to be another way to perform an attention mechanism is the non-local layer, right? So we want to create attention not based on weights, because this is non-local as well, but we want to create this relationship between elements. How much should each element contribute to the representation of each other based on the relationship among them. So we're going to be using some function that computes the affinity between every pair of elements, and that is going to decide the weights, not a pre-trained network or whatever, right? Hopefully this will be more clear when we get into the transformer per se. Okay, so let's do this. We're going to get into the transformer. You probably have already seen this graphic somewhere in the network, in the internet. We have a lot of things going on here, so let's unpack them bit by bit. First of all, the transformer is going to take an input, which is going to be a sequence. And this sequence, we want to divide it into elements. We will see this in a bit. It's going to be, if given an image, its elements are going to be the pixels, for instance, or given a sentence, the elements are going to be letters or words or something like that. So we're going to give it separated by those elements, which means we're going to tokenize it. Then transformers don't know anything about position, right? So the transformer is only going to see a bunch of elements going around, a bag of elements. So we need to add positional information to tell them relative positioning between the elements of the sequence. And then we start with the proper transformer layers, with these gray boxes here. As you can see, there are 3 main components here. We have the multi-head attention, which is the core idea and is where the non-local operation of the attention is going to happen. This is the most important part. We have a feed-forward network, which is a normal multi-layer perceptron, right? And then we have residuals and normalization. Residuals is where we are going to take the input before the transformation here, and we're gonna send it exactly the same up to here. We're gonna sum it to the output, and then we're gonna apply layer normalization. So we've got these 3 components, right? So I want to get out of the way first the feed-forward network. This is going to be just matrix multiplication. We're going to take the input, multiply it by a matrix. This is a normal feed-forward layer. Add a bias, no problem here. The only particularity they have is they're going to be point-wise feed-forward networks. What this means basically is we're going to be applying the same transformation independently for each of the input tokens in the sequence. So we are not applying it to all of the input at the same time. We're applying a transformation individually to each token of the sequence. Okay, now let's get into the important matters of the transformer. So we're going to have this multi-head attention, right? What it means for it to be multi-head? Well, simply it means that we're going to perform different attention operations. It's not going to be just one. We're going to map the representation of the input into many different representation spaces, right? Similar to what we did with convolutional filters. If you recall, one single convolutional layer had maybe 32 convolutional filters, and we would apply these filters over the image, resulting in 32 different outputs for that convolutional layer. Here we're going to do something very similar. We're going to map the input to different representation spaces and perform attention there, so we are able to attend at different things in the same regions, right? Then we're going to concatenate the output, and we are going to map it through a linear transformation back into the common representation space. Okay, no problem here. Now let's get into the actual non-local operation, this scale dot product. What are we going to do? Well, we're going to map the input into 3 different representation spaces, which are going to be called queries, keys, and values. And we are going to perform this operation here, which is the self-attention operation. Okay, let's get to see it a bit. If you recall what I have been saying, a non-local operation is a mechanism that we're going to use to route information from every token in the sequence to every other token. So each token needs to be able to access information from all of the elements in the sequence, right? And we're going to use this to create a weighted contextual representation of each token, right? If you recall, we're going to decide how much should each token contribute to every other token. And we're going to do this with queries, keys, and values. So we're going to take the input. This is a sequence of 6 elements. Each element is going to be represented as a vector. And here I draw the vectors as numbers, but here the vectors are represented as 2-dimensional arrows, right? So imagine this is the input representation, and we map it through linear layers to 3 different representations. The query is going to represent what each token wants to know, right? What information does this token need, or each of them? Then the keys are going to represent roughly what each token has to offer, so relevant information that's contained in the token. And finally, the values are going to represent what does each token actually contain, the information contained there. The representation of the sequence is going to be better encoded here. So what we want to do is we want to compare the keys with the queries, right? We're going to do this by simple dot product. We're performing here a dot product. And what we're doing, for instance, imagine we're trying to see this query in particular, and we want to compare it with every key. And when we compare them with all the keys, we see that this query in particular is quite similar to this one, and roughly similar to this one. So what we're going to see in the output is that, okay, that query was very similar to this one and roughly similar to that one. So we're going to get these histograms of similarity, right? So how similar was the first query to all the keys? We get this output. How similar was this query to all the keys? We get this output, etc. And we get this attention matrix, right? The softmax is here to actually turn them into probabilities, and hence we can call them an attention matrix because it all is going to sum up to 1. But I want you only to get the main idea here, that we're comparing one with the other, and we get this distribution of relatedness between all the queries and all the keys. And now we're going to be using these weights to create the new representation for the values, right? So the representation of the first value is going to be using these weights to sum all of the values and get the resulting new representation that grabs information from all of the other values with these weights. So for instance, in this case, we're going to get a value representation that's mostly looking like the 4th token, so the one pointing to the right, a little bit pointing upwards because it's this one here, and then a little bit of the remaining of them, but mostly these ones, right? So we get an arrow that's mostly pointing to the right and a bit pointing a bit up, which is here. So we get a representation for each value that is dependent on the information from every other value, hence the non-local operation. And we get the next representation, the representation for the next layer of our sequence. So this is the idea of queries, keys, and values attention. So to summarize, we're performing this scale.product where we map the input to queries, keys, and values. We perform some scaling operation that's going to help us normalize the results. Some masking, we will see the masking in a bit. and then the softmax to turn the activations into probabilities and actually transform into an attention matrix. The main idea behind the dot product is this idea that if we have two vectors that are linearly independent, the dot product is going to be 0. And the more related two vectors are, the higher the dot product is going to be. That's why we can use them, this operation, the dot product, to compare two sets of vectors. Okay, so this has been the transformer. Now let's see some example to see the transformer in action. I hope this helps make it a little bit clearer. I'm going to make some simplifications in this example. Also, I'm going to be using machine translation from text to text instead of a vision example, because I think it's going to be easier to understand everything. And also bear in mind that the main difference between vision transformers and text transformers is not going to be in the architecture of the transformer itself. In the self-attention layers we've seen, that's going to be exactly the same. The main difference is going to be how we tokenize the input, the embeddings we use, and maybe positional encodings, but not even that. So let's imagine we have this sentence as input and we want to translate it to French, right? So the first step is tokenize it. In this case, we're going to separate the input into different words, right? That's our tokens. In computer vision, what we would do, the first attempts to use this were tokenizing input images with pixels, right? So every pixel would turn into a token of our input sequence. But this is going to be a problem because, as we will see now in a bit, attention matrix is going to grow quadratically with the input sequence length. So if we have an image of 256 and 256, the attention matrix is going to end up having roughly 65,000 squared elements. That's a huge matrix. We don't want that. So in practice, most transformers for images are going to be using patches as tokens, which are going to be small regions of the input, in this case, a 3x3 patch, right? So patches. And what about videos? Well, for videos, it's going to be the same. Some have tried to do this patch thing, and this patch thing is going to be interesting because it's going to allow to create relationships not only in time among different frames, but also to create the spatial relationships, to learn representations within the frames. But this is going to be problematic, again, if we divide each frame in the video into patches and we stack all the patches from the different frames, we're going to end up having also huge attention matrices. So we don't want that either. We can solve this problem somehow trying to use 3D patches, which instead of patches covering only one frame, we are going to have patches that also span across several frames, and we stack these volumetric patches, but still we're going to have a lot of elements in the attention matrix. So in practice, what we're going to see most are video transformers that are going to be using frames, individual frames as tokens, or even small clips of 1 second, 3 seconds, something like that, as individual tokens. So, okay, this has been tokenization. Back to our example, we already have our input tokenized. The next step is running our individual tokens through an embedding network. An embedding network is simply going to be generally a convolutional network, or sometimes it's going to be a multi-layer perceptron. In the case of text, word to vec, which is going to transform a word to a vector representation. In vision, we're always going to see, or most of the time, we're going to see a convolutional network, which is going to transform each individual patch or frame or whatever into a vector representation here, right? Next thing we have to do, as I was mentioning before, transformers don't know about position. So, as they do not know about position, we need to add this information. So we need to tell them, okay, this token was the first element, this other token is the second element in the sequence, this is the third element in the sequence, and so on. We need to add some information to tell them relative position between the tokens of the sequence. Also importantly, as we want to add this information, we're going to need the representation of this one and of this two to have the same dimensionality of the vectors representing each token. So what can we do? The first thing that maybe pops to mind is using a binary representation, right? So imagine that our vector representation has 4 elements, so each token is represented with 4 numbers, So we could add just a binary representation, right, with ones and zeros and so on. But if we're using this discrete representation, only ones and zeros, we're going to run out of numbers pretty quickly, right? With 4 elements, we can only represent sequences up to 16 elements. So in practice, what we're going to do is to use a set of sinusoidal functions with different amplitudes, different frequencies, to to create this vector of positional information, right? So for instance, for the 40th token in the input sequence, the dimension 7 of the positional encoding is going to have minus 0.75, and then the dimension 4 is going to have roughly a 0, the dimension 6 is going to have 0.5, and dimension 5 is going to have around 1. So instead of zeros and ones, which is a discrete representation, we're going to have this continuous representation. So we're going to end up with, well, this is a formula actually, where we have, this is going to be the token, the particular token, this is going to be some parameter controlling the frequency, and this is going to be the dimensionality of the token representation. So we're going to end up with these kind of vectors, right? So this is going to be the position information for the first token, for the second token, for the third token, and so on. In images and videos, we're going to have the same. In general, we are going to see positional encodings using raster order, meaning that we're just numbering the patches of an image or the frames or whatever in these directions. So we're going to or the first row, then the second row, etc. We do not need necessarily to use 2D coordinates, although some works use this representation. It's not very common, and the works that have tried to compare both have ended up saying that there's not much difference. So using 2D, roughly what means is to take 2 of these vectors and just concatenate them, right? Put one after the other. The same goes for 3D, which could only be used in the case of video, where we are using patches as tokens. So this is the third frame, the second row, and the second column of that frame to indicate that this patch in particular has that position. But this is not very commonly used. Mostly we use just the raster order. Okay, so we already have this positional encoding information added. So we have a final representation, each token with the corresponding position. We already know everything we need to know. Let's get into the transformer. So, as I was saying, what we're going to do is going to map the input representation into queries and keys. We're going to perform the dot product, and we're going to compute this affinity, this attention matrix, which is going to tell us how related each token is to every other token. So for instance, the word once, we can see here that it's super related to itself. As we can see in this diagonal, every token is going to be super related to itself, but it also is very related to the word cat, because cat is the one that wants something. Or another example, the word eat is very related to the cat, because the cat is the one that's going to be performing the action, and pizza is the thing that's going to be eaten. So we see the relationships among the elements, and we're going to use this affinity attention matrix to weight how much should this value contribute to each other, and we're going to get this new representation, which now, because here, if you recall, we had only individual information for each token. There was no information flowing between them. But now we have contextualized information, right? So this token now has information not only about the first word, but about every other word, okay? Now we're gonna have several layers like this. So this is going to be used as input to the next layer. And as you can see, I'm doing several simplifications here. So I have not included the residual connections. I have not included the point-wise fully connected layer. I'm simplifying the example to just the self-attention layer. Okay, so we said we wanted to translate. We already have a representation, contextualized representation of the input representing this sentence. Now we want to decode, right? We want to create a sentence in another language. So we're going to be using, instead of self-attention we've been using here, we're going to be using cross-attention. So we're going to just use some information from another side to request information from this encoded representation. So we're going to take this as input, and we're going to be using the output of the encoder as keys and values, but the queries are going to come from a different side. So here we're going to be using this special token designed to represent that a sentence is starting, and we're going to be performing exactly the same steps as the input. We're going to run that word through a embedding network. We're going to add positional information, and this input is going to be used as queries to request information from the encoder output representation. So we perform the same dot product to see how much this query is relevant for every key. We're going to get this affinity matrix. This affinity matrix is going to be used to weight how much should its value contribute to each other, and we're going to get an output representation. This output representation is going to be fed through a linear network, and we get the output probabilities for every word. And in this case, the most probable word given this query and this sentence representation is going to be this word. So we're going to be using an autoregressive decoding strategy, which means that we're going to take the output and we're going to be using it again as input. And with these two words, we repeat the process, we query for information from the encoder. This part hasn't changed, it's exactly the same representation. And what is changing is this part here. And we again compute the attention matrix, get an output representation, process it again, get another word, and repeat the process over and over again until we get an ending token, like a sentence ends here. Okay, so this has been the transformer. This is the main idea. We've got self-attention and cross-attention, positional encodings, embedding networks, and tokenization. This has been it. So there are a lot of different things we can do with this. And the first models showed impressive results in natural language, even allowed some people to build an artificial master for Dungeons and Dragons. So the network was telling you a story, you could take some actions, and depending on the actions you took, the model kept telling you the story and the story kept evolving. But it was very impressive by the fact that these models were very able to not only to remember, but to also be able to know a lot of information. So GPT-2 was this model, this transformer model, huge model that was trained on a lot of text from the internet. So given this input prompt, it was told that some unicorns were found somewhere in the Andes mountains, and it was even able to understand where the Andes is and telling us that the University of La Paz, and at some point the name of the doctor finding the unicorns was a Spanish name. So it was able to make sense of a lot of this information. It was able to learn a lot of interesting long-range relationships among the input. This has also been extended to image models, where you can, text-to-image models, where the network has been perfectly able to understand relationships about different elements and characteristics of them. So for instance, it has learned what a turtle is, what a forest is, and it has also learned climation, right? So it's three different elements, but it has learned how to combine. Even if it has never seen a climation turtle, it understands properly what a turtle and climation is, and it's able to merge those two ideas. You can even go online and play a little bit with this tool and see the different generations. And when we train these kind of models with online internet information, it even starts to learn some patterns of memes online, and we can see these interesting things. It's maybe not as sharply generated because this is some internet random generation, while these ones were by OpenAI, which is a more big company, right? But we still see some trend going on here. And even complex, abstract images. And now looking into classification results, we can see that these new transformer models have been able to solve a lot of different benchmarks of classification, achieving new state-of-the-art in many different benchmarks. And for video, we see a similar trend. We can see that these models, which we will see later in this presentation, have achieved new state-of-the-art in classification, action classification for kinetics and different data sets. We can see new state-of-the-art in everything. So transformers are achieving a lot of things. We have already seen all this information about more general transformers. Now let's get into transformers for computer vision. So to understand the main differences between the natural language processing transformers and the computer vision transformers, we're going to have to look to some of the limitations that transformers have. So first of all, transformers are going to be highly parametric. What does it mean? Okay, it has a lot of transformation matrices. Each head is going to have its own transformation for queries, keys, and values. We're going to have this matrix that is going to be mapping back all the different heads and the point-wise feed-forward layers. So by taking up the parameters used on the original transformer, this was the dimensionality of each token, which in computer vision is going to be a bit higher, doubling or the triple size for each token. Having each layer 8 different heads. C is this mapping to higher dimensionality space and then back to the same one in these layers. Each layer is going to have roughly 2.5 million parameters. If we have 6 layers, we very quickly have 14 million parameters. For the sake of comparison, here in this table we have a convolutional layer, a very a very commonly used convolutional architecture, which is the ResNet. And when it has 1,000 layers, we're going to have 19 million parameters, which is almost there. Computer vision transformers are going to have this to be much higher. So we're going to very quickly scale up to a lot of parameters. Also, transformers, and we've mentioned something about this earlier, don't have any inductive biases, right? That's why we need positional encodings. They don't know about position the way that convolutional networks do. They don't know about translation equivariance, while a convolution very quickly understands that a corner means the same regardless of where in the image the corner appears. Transformers don't know that. And while a convolutional network knows that local information is the relevant information, transformers do not know. Transformers are looking at every element in the sequence and do not know anything about the importance of local relationships. So it's going to need to learn everything from the data. So we're going to need a lot of data to be training these transformers. We're going to need a lot of data to ensure that the model does not overfit. Given that it has so many parameters, it's going to be very prone to overfitting. So we're going to be needing to train a lot, to use a lot of GPUs, a lot of energy, a lot of CO2 emissions and everything that comes with it. So how do we solve this? First of all, we're going to be sharing weights. So most transformers nowadays are sharing weights, which means that we have less parameters to train. We have models that are less prone to overfit, and it's going to be easier to train them. But also some works have found that reducing the number of parameters is helping to achieve better results, which may be related to less overfitting side of things. But also we're going to be using pre-training. You already saw last week this self-supervised way of doing things. We're going to be looking at some of these techniques applied for transformers as well. So first of all, weight sharing. The idea is going to be that we are going to have the same parameters across transformer layers. So for a given layer, we will have these matrix transformations for each head, but those matrix transformations from input to queries, keys, and values are going to be the same across all layers. We see here an example that it's not only doing weight sharing, but it's also doing matrix decomposition, which is also going to help our cause of having a more efficient transformer. I'm not going to get into details about this because it's quite mathematically complex, but the main idea is we're going to approximate each weight matrix with 3 matrices with which we are going to multiply by itself. So in this example, in this work that I'm showing here, they had a multimodal transformer. So they had one stream for video information, one stream for audio information, and so on. So they tested several different settings for weight sharing. So first of all, no sharing. So each layer had its own weight. Then sharing across all the layers of a given modality for the video and for the audio. Then sharing everything. And then sharing with this matrix decomposition, in which they only share the big matrix here, while these 2 matrices, which are smaller, are independent for each modality. So you can see here that they start off with only 2 layers, not sharing at all, and already 7 million parameters. Then they go up to 21 million parameters, but because now they have 6 layers. But Each modality has its own weights. Now from here we're going to go down. When everything shares parameters, they only have 7 million parameters again, but the results keep improving. So from 21 million parameters, then we have gone down to 75% accuracy. And now when sharing with this matrix decomposition approach, they end up having only 4 million parameters and the best results so far. So this is going to help a lot of cause, and most transformers nowadays are sharing parameters. Now, regarding the pre-training, you already saw the idea is going to be that we first are going to train the model with a lot of data from the internet, a lot of images, a lot of videos, whatever, and we don't need labels for those. So that's what it's going to allow for them to be as huge data sets. And the idea is we want to learn internal structure of the data. We don't, so far, do not learn any task-specific information. So the idea is the network is going to learn that some objects have this structure where there's a lot of green things up here, and then down below there's some brown thing, or in this case there's this furry texture with some pinkish thing here and black stuff over here, 2 dark dots and 1 here. And okay, it's learning some structure of the data. They do not know anything about this is a dog or this is a tree. They just know this structural information. And then we're going to do the fine-tuning for a downstream task, meaning that we're going to use label data set, which do not need generally to be super big, because making labels for a data set is expensive. And we're going to be learning with that pre-learned structural information of the world. We want to be learning relevant task-specific information. So we're going to be teaching the network that that structure it had already learned, it's a tree, and that this structure is a dog. It's going to be easier once this internal structure has already been learned. Okay, so which tasks are transformers using for images to pre-train these models? So one of them is going to be reconstruction. As you can see here, what we're going to do is to use the image itself as the labels, right? So instead of telling the network, okay, you'll have to learn something about this and then classify something, we're going to be teaching the network to reconstruct the input. So each pixel is going to be a label in practice, yeah? So what we're going to do is to grab the image, we're going to be adding some noise here, and with this noise, what we're going to do is input each of these patches as tokens to the transformer, and we're going to take the output representations and we're going to rebuild the image and just compare it pixel by pixel with the original image. And we're going to tell the network that it should have better, because you can see here missing all these trunk thing and all the ropes, etc. So by trying to reconstruct the original image, we force the network to learn the internal structure representation of, okay, there should be a bird here. This bird is probably having to stand on top of something because I'm getting a strong supervision telling me that there's a lot of mistake going on here. So it should have been something here, etc., etc. This is one of the most common tasks, but we are also going to see a lot of other things. You saw last week contrastive learning, in which we have a positive pair in which the two images are related, and we have a set of negative pairs in which this image is not related at all with the other elements. So for instance, in here, well, this is another example of supervised contrastive. Well, but the main idea is that we want the representation of the elements that are in the positive pair to have a similar representation, and the elements that are in the negative pair to have a very different representation. So what we're going to do, okay, so for images, the main idea is going to be mask prediction, right? But as we cannot directly predict the patch because that's going to be expensive, what we're going to do is use these contrastive laws. But instead of using two similar things, we want the contrastive representation to make the input of a specific token and the output representation of that token to maximize mutual information, to have as much more shared information as possible for the positive pair, while for the negative pair, the output representation of the selected element has to be different. We want the representation to be different from the other input tokens. So similar to the actual input token, and different when the tokens are different. So what we're going to do for images, we're going to delete the information. We're going to mask the information from one of the tokens. We're going to feed that to the transformer. We're going to take the output representation, and we want the transformer to grab information from all of the tokens, make that information flow into this token, and create a valid representation even if no information was present to begin with. And what we want to do is to compare the similarity between that output representation of the token that was masked with the input representation of that same token. And we want to maximize the cosine similarity in this case. This particular example was using frames for video. One of the frames is going to be masked, so no information from that frame. And then we want the representation of that frame to grab information from every other present frame and reconstruct properly that information. And by trying to tell the network, okay, the representation for this output should be as similar or sharing as much information with the actual input token, we're forcing it to learn the internal structure of the data. Similarly, another thing that's done is to shuffle the input, right? So we're going to be telling the network, or in this case with our positional encodings, that this is the actual input, right? So we tell them, okay, this is the input. But the network has to be able to reorder the patches properly, right? So instead of actually reconstructing the whole image, it is cheaper to just classify the output tokens in the proper order, right? So what we do is to create this initial representation, then we reorder the tokens, and then we take the output representations and we train a classifier to be able to properly classify the tokens in the correct order. So this one the first, the second, this is the seventh token, and so on. So by learning to properly order these tokens, we are teaching the network how things should be, what the proper structure of things should be. So it's learning the internal representation of the data. Now, finally, another unsupervised or self-supervised approach that is used in transformers is momentum contrast. This is a fairly new type of procedure to train a model of a loss that is combining information from knowledge distillation, data augmentation, and contrastive self-supervised approaches. We have already seen contrastive self-supervised approaches. Knowledge distillation, I think you already saw something like this. Very quickly, the main idea is we have a large network that has already been trained for a task, and we want a smaller network to solve exactly the same task, but to solve it as well as the big network while having many less weights. So what we do, instead of using these categorical very hard labels like everything is 0, the probability of this input being this class is 0 and this class is 0, but being this class is 100%, we're going to use the softmax probabilities of the output of this network, which is telling, okay, this could be 0.07 a cat, 0.13 a tree, but 0.61 it's a dog. So I'm mostly sure it's a dog, but I have some doubt among these other classes. So when using these soft labels to train the smaller network gets better at solving the task than if using only the hard labels. So this is knowledge distillation, like transferring this information to the smaller network. And then the idea of that augmentation is to take an original image and create these different small patches, right? So small crops, we can flip the image, we can rotate the image, we can do zoom in, we can skew the image. So this is that augmentation. And what we want with this contrastive idea is that we want the representation for all these patches to be very close together, because we know they come from the same image, right? So the representation should be very close together. So with this, you already saw last week the BIOL method, in which the teacher network and the student network are going to be trained at the same time. So a very similar model arises in transformer models, where what we're doing is we have a teacher network, and we are going to feed it the whole image, and we have several augmented versions of the image that we're going to be feeding to the student network. And now, what we want to predict is some distribution of softmax probabilities, not necessarily a class, but the main idea is that we want the distribution of probabilities here to match the distribution here. Now, the interesting thing is that the teacher network in this case is not going to be pre-trained. We're training both roughly at the same time. So gradients are only going to be flowing through this, and with some interesting tricks of the estimated moving average and the centering, which I'm not going to get into, through these two interesting tricks, we're going to transfer the weights from the student to the teacher after some iterations. So we're going to train the student to match the representation of the teacher, and then when the student has been trained, we transfer that information back to the teacher somehow, and we create an average of all the networks, of the weights, sorry, on the teacher. And just by doing this, when the student and the teacher are transformers, you can see here, these are the attention activations. So the network is already discovering by itself. This is not trained for segmentation or anything. The network is already learned to pay attention to relevant objects in the images just by this training, right? By trying to match a network that's roughly itself. Okay, so this has been the pre-training methods that are going to help us train all those parameters in transformer models with all this big data without the need of supervision. So now let's see what things can we change in the design of the transformer to make it more efficient. Another problem that is not specifically related to the parameters is going to be the size of the attention matrix. We have already talked about this when talking about tokenization, is that the problem that the attention matrix is going to grow quadratically with the number of input tokens. So if you recall, we're going to be performing this dot product, which is the input sequence times the input sequence. So we're going to get an attention matrix that's the input sequence length squared. So this attention matrix can grow exponentially with the size of quadratically with the size of the input sequence. So this can get to be a problem because transformers can adapt to any length of input, but this attention matrix that needs to hold in memory is going to be limiting this capability. So what we're going to do mostly for visual transformers is going to be sparse or decomposed approaches. In summary, what we're going to do is to limit the number of tokens that can be attended at a given attention operation. So first of all, we have the locality or sparse approaches, which what we're going to do. The local is going to allow to attend only to neighboring tokens. So each token is only allowed to look to a neighbor, to a set of neighbors. And the sparse is going to allow to look at distant tokens, but not all of them. So maybe every other 2 or every 3 tokens I can attend. So for instance, we can see here in this design, we get a small query block. So the queries are only going to come from this block, and keys and values are only going to come from this other block. So this is going to move as we advance. In this case was for a decoder. They are generating an image. So when generating, we are only going to be looking at this small set of pixels as queries and this small set of pixels as keys and values. Keys and values are sometimes called memory. Here is 1D and here is the same idea for 2D. So the idea is that when using queries from this block, I can only attend to this neighboring set of pixels, right? So I'm restricting the attention to be local. And by this, I'm reducing the number of tokens, hence the input sequence length, and hence the attention matrix is going to be smaller. Same idea here, where we perform 2 separate operations, one local operation and one sparse operation. So this is going to be the tokens in the image that I'm attending, and this is going to be the attention matrix actually. So the gray areas are not computed. And by only computing the blue ones, I'm reducing the number of operations, and this is going to be easier to store in memory. So I'm looking first at a local set of elements, which is only when this is the query, I'm only looking at a local set of elements. And I'm also allowing the model to look in distant positions, but sparsely. So I'm not attending to this tree, I'm only attending to this one. And by doing the two operations one after the other, as we'll see in a bit in the composition, we're going to achieve an approximation of the full attention. Finally, yes, again, as I was saying, this is for, instead of for images, for video. Still local and global attention, but the local is going to be dense, while the global is going to be sparse. So imagine we have the current frame, right? So for this particular, well, decomposing the attention, in this particular example, this would be the query. This query is allowed to attend to neighboring pixels, so all of these pixels, and in the previous frame also capable to attending to all of these pixels and all of these pixels, right? But as I go further in time and space, I can only look to a sparse set of pixels and I can't go all the way. So I can only look at this and this and this, but not this or not this. And the same goes here. The same idea for video, as I said. Now, I was saying that this idea of performing several attention operations one after the other is approximating full attention. So the idea is going to be like, when I perform full attention, every token is attending, in this example, at 9 tokens, right? So this token is attending to all of the other 8 tokens and to itself. So it's allowing information to flow from every other element up to here. So when the result is going to be that all of the tokens have information from every other token. So in this case, in this particular example, the attention weights have been uniform. That's why the information contained in every token is going to be exactly the same. In practice, it is not going to be like this. I just wanted, I used uniform attention weights to illustrate this idea. When we use the composed approach, in this case, is an axial attention, where we first perform horizontal attention and then vertical attention. Each attention operation here is only involving 3 tokens, right? So this token is only able to attend to this row, this token is only able to attend to this row, and this token is only allowed to attend to this row. And the same goes here and here, but for the middle tokens and to the right tokens. Then we get this representation, and then we perform vertical attention. So now information has already flown in this direction, and by the time that we are performing vertical attention, the horizontal attention has been distributed across all of the tokens horizontally. So now when we perform the vertical attention, we also end up with a representation that allows information in this token to come from every other token somehow. And while the representations are not going to be exactly the same, we can say that with this approach, we have performed attention operations that were smaller, but have ended up approximating full attention by decomposing it into approaches. So now we can see this in both video and image. In image, we see here we perform first one operation, followed by another axial operation. And for instance, here in video, we first perform time attention, in which this token is capable to attend to all of the tokens that are in the same position, but in previous and following frames. So now that I have aggregated all the information for this token across time, now I attend to all tokens in this row. So when this token is looking at this token has already aggregated information from the previous representation from the previous frames of that same token and for the following ones. So this token is actually attending to this token through these two set of attention. And the same goes when afterwards we perform the attention across the height axis. And then finally we have the spatiotemporal decomposition, which only makes sense when we're using patches for video. In this example, we can see only spatial attention. Each token is only allowed to access information from tokens in the same frame. Joint spatiotemporal attention is the full transformer model without restrictions, like every token is allowed to access to every other token. And then we have the decomposed time attention, right? First time and then space. So as I was saying, the same goes when I explain the decomposed axial for video. The idea is that this token first aggregates information from its past and its future, and then every token can attend to every other token within the same frame. This spatiotemporal decomposition can be done in several ways. So for instance, we can have a transformer layer which has first a spatial attention block, then a temporal attention block, then the fully connected layer, and then etc. We go out. We can also do a hierarchical approach in which we first perform spatial attention for each frame independently, right? So for this set of tokens that are for the last frame, for the second frame, for the first frame, and then we gather that information and perform attention on the temporal axis, where each frame is able to access information from each other. And finally, we can also have separate heads, so a set of heads which are only allowed to attend to information from within the same frame, and temporal heads which are only allowed to flow information from within frames, but not to look within. And yeah, finally, the other efficient designs, I already mentioned some example of hierarchy, but the idea is going to be reducing dimensionality as we go on. So first, we have this set of transformers that are going to be looking, in this case, to individual tokens, in this case, frames. So we're going to be creating relationships among small sets of frames. So we're going to be looking at a small clip here, the following clip, the following clip. And then we're going to perform some aggregation operation that is going to create a whole clip representation. And then we're going to be able to create these interclip relationships, right? So by doing first relationships between small elements and then between the bigger elements, we get something similar to here. This is going to be hierarchy. It's also going to help us reduce parameters, to make it more efficient, to reduce the size of the attention operations, because we have smaller sequences at each individual transformer, etc. Okay, so this has been all of the transformer specific designs that we can get in Vision. Now let's see some examples of Vision transformers. First of all, the Vision transformer. This is probably going to be the most useful architecture you can get for images. It was the first to decide to use patches as tokens instead of pixels, and it got amazing results on classification. So some of the tables I showed you at the beginning with new states of the art are from this publication. Some of the key elements is they place the normalization before instead of after every sublayer. And also, this is not their original contribution, but this is important to mention, to use an extra token, which is generally called the class token, which the main idea is going to be that we're going to only use the representation from that extra token for classification. And by forcing the gradients to flow towards that token, we are forcing the transformer to gather the information from the whole sequence, from all of the tokens, onto that token here. So this is going to be like an aggregated representation of the whole sequence. Okay, now going from there's this work that tried to reconstruct a mesh given an input image. Some of the key contributions were this dimensionality reduction, which is very uncommon to see on the transformers, up to reduced dimensionality, we get a three-dimensional representation for each token, which are going to be directly the joints of the skeleton and the position of each vertex in the mesh. And then another very interesting thing of this work is the use of the positional encodings. So instead of using different tokens, each token is going to be exactly the same. So this is going to be a vector representation of the image output from a CNN, and we're going to replicate that vector across all of the tokens, and the difference is going to be in the positional encoding. They are going to define a template skeleton and a template mesh, and the positional encodings are going to be the position of each of the joints and of each of those vertices. They're going to be performing this masked token prediction. It's like trying to reconstruct a missing information. And that's it. And with this, they achieve very impressive results when looking at trying to reconstruct the mesh from an input image. Now, the transformer for object detection, very quickly, they create a vector representation of the input. They add positional information, and then they're going to be using these tokens, which are going to be pixels, kind of, but of the output, not of the input image. They're going to run it through a transformer encoder that is going to create a non-local contextualized representation of the input. And then the decoder is going to use a set of queries that are going to be learned. So they are going to train the initial representation of these queries, and by a set of transformer layers that iteratively attend to this information, we're going to get a set of potential object representations. They run it through a linear layer, and they get position and class of each box. Some of them could be of no object, so some of these queries not necessarily needs to match an object of the image. This was easily extended to segmentation, where we do not want the box, but we want a classification for each pixel. And the main difference is this is for video, so they're going to use a subset of the queries for each frame. The input idea is going to be the same, and then they are going to use this instant sequence matching and segmentation to end up matching each regressed object to the same ones across all of the frames. Then, not necessarily using video or image or frames or whatever, in this vision work they were trying to classify action recognition, but given only a sequence of poses. So here we would have a man or woman raising the hand. They had this decomposed approach here where it had spatial self-attention, where each joint was only able to attend to all of the joints within the same skeleton frame, and then they had temporal attention, where each joint was only able to attend to the same joint but across time, right? And instead of doing this decomposed approach where they do one first of the spatial followed by the temporal, they did two streams, one that modeled spatial relationships, one that modeled temporal relationships, and then they combined the predictions of both for the action classification. We also have the video action transformer. The interesting thing here is how the queries were used. So first we use an input clip, we run it through a 3D convolutional network, and we get an output volume representation for that video. And we're going to take the middle frame, and with that middle frame we want to run it through a region proposal network, generally used for object detection, but we're going to get like relevant regions of the of that input. And those relevant regions is what we are going to use to create an initial query representation. This is going to be a query which is going to be very small because it's only relevant regions for the central frame. But then we have the keys and values that are going to be using the information from all the video, all the volume information. So we are going to keep keys and values exactly the same, and we're going to get the query to be evolved, right? So we're going to use this query to attend to all that information, and we're going to get as output a new query, an evolved query. With this evolved query, we will attend again to the same information. By this iterative attention process, we're going to end up having a query representation that is good enough to classify the action, but also to regress the position of the bounding box where the action was happening. With a similar idea, the perceiver was proposed, by which we get a latent array. So again, we have a query that is learned, the initial representation is learned, and we're going to use a very small query to access a huge information of the input. So this could be an image, it could be a video or whatever. It's a lot of information, huge dimensionality. And in order to reduce the size of the attention matrix, we perform this small query attends to huge data here. And the keys and the values are going to be the same across all the attention. It's not going to change the input. What we are going to change is the representation of the query. That's what is going to evolve. So again, we're performing iterative attention. We're iteratively attending to the same input, and every time we attend, we learn new things about this input. And we get two things: the cross attention, where the query is attending to the input, and then the latent transformer, where the query is performing self-attention on itself to get evolved. This was successfully used for both images, video and audio, etc. A lot of things. This is super interesting work. And finally, one of the few works, there are some other out there, but some of the few work that actually perform low-level image reconstruction is this work for inpainting, where they took a target frame and they wanted to reconstruct the missing content here. They took a set of locally dense sampled frames and sparsely sampled frames further away in time. And the main contribution here was using several heads, where each head was processing query keys and values at different sizes, right? So in this scale, the patches were bigger, and as we get down to other heads, we have smaller patches containing more information, but in a smaller resolution. And they perform query keys and values attention, and at the output, they use running through a convolutional network to get the reconstructed output frame. Okay, so this has been it. As you see, transformers are very complicated to train. They need a lot of data, etc. So mostly what we need to do if we want to use them is to rely on pre-trained models. A lot of works upload their pre-trained works to GitHub. So you have to keep looking at the repositories of the works that you want to replicate to see if you can use their weights, because training from scratch in the comfort of your home is going to be complicated. Also, Colab from Google Collaboratory allows you to use some GPUs if you don't have your own, so this is going to be also useful. And then, as I was saying before, the Vision Transformer is available on Hugging Face. Hugging Face is a site for sharing pre-trained models, so everyone can have access to them, and you don't need a huge compute power to train the models on your own. And it's generally for natural language processing models, but they have included this Vision Transformer. So that's probably one of the reasons as well, because why this model is getting so widespread out there. So this has been all from my side. Thank you very much for attending, and yeah, have a nice day.